Other evidence, this, we already saw this. Let me see this one. No, sorry. Let me go to there are many pictures on the web, and yes. This is what I wanted to show you. This graph refers to the United States. And again, you see, it doesn't seem that there is a clear tendency. And take-home message, changes in temperature are clearly visible. Changes in rainfall everywhere are not clearly detectable, and there are no clear tendencies, and the tendencies are evenly distributed over the world. Means that, for instance, in Northern Europe there is an increased water resources availability. In Southern Europe there is a light decrease. So basically it's not clear what's going on. In terms of water resources, there is a clear effect on where water resources depend on snow melt. So in this case, indeed, we observe a change in the river regime, which is related to the fact that indeed there is an earlier snow melt in some, for instance, in the alpine regions, and the overall regime is affected by the fact that the temperature, especially in the Alps, is increased. But other than in the regions where snow melt is dominant, we don't see on water resources availability a clear tendency, which is to be expected, because if we don't see a clear tendency in rainfall, then we don't see big changes in the water resources availability. And I want to show you some graphs that refer, I'm not sure, maybe that I already showed them to you, refer to the Po River, but they are indeed significant. Just 1 second. First of all, what you see here, look at the title, these are the daily river flows over the Po River at Ponte lago Scuro, the closed section, as time passes, and this is the overall average. And when you look at these pictures that are moving forward, you see that there are cycles here. There are periods where the yearly average is below the mean, and periods where you can find a stable situation of river flows above the mean. But it's difficult to find a clear tendency. So even when you reach recent times, you see that there is no clear tendency here. It's sometimes we have dry periods and sometimes there are floods, but it's not really. For instance, around 1980 there was a high flow period, and but the tendency is not really clear. We see a couple of floods in 1994 and 2000. They were quite heavy flood, the last one here, and then 2000, again around October, will be here, you see here. But then you see in the other years, we didn't have any flood. And this was something that I insisted a lot. Usually people look at global series, so basically when you put together a very huge amount of data in only one graph, you don't see anything. And I said to my colleagues, let's look at the single years, because otherwise we don't see anything if we put all the data together. So this is one first graph, and then this is a regression line over the maxima. These are annual maxima of the Po River from 1920. This is repeating, so you're not missing anything. From 1920 to 2010. Basically, what I did here is to compute linear regression over a moving window which is 50 years long. So basically I took the first 50 years, computed the linear regression depicted there, and then from year 2 to year 51, linear regression, and this is the resulting regression. Keep in mind that 50 years in water resources are deemed to be a very long period, so you are very lucky if you can estimate the river regime over 50 years. So these are very reliable regressions compared to what people usually take advantage of from when designing. Now, if we do that and you depict in blue the increasing tendency and in red the decreasing ones, you see the difference and you see that there is a lot of uncertainty. And keep in mind that the maxima, according to climate change, should be always increasing. So basically what do you see here? You see that there is a lot of uncertainty. You see that the line becomes red around the 80s. And then in the last period, there is again an increase. But you see that you never see a clear tendency. If you compute the overall regression, it is slightly increasing. And if you compute the overall regression by rejecting the past 20 years, is slightly decreasing. So can you see really an evident tendency here? And now let's look at the minimum. I had a discussion with the Environmental Agency. They said that from 1980 to today, we have 20% less water during summer in the Po River. So I went there and I took the annual minimum, not the annual maximum, the annual minimum. Let's compute the same exercise, because indeed they say 30% less. So let's see. So this is the minimum. And you see how much uncertainty there is there. And then, indeed, in the last period it becomes red, but it becomes red just in the last period. And then I made an experiment. I computed the rate of decrease from 1986 to 2007. And indeed, you find a change of 30%. So they were right. But then I added 2 years, and the slope became positive. So the change became positive. What does this mean? It means that there is a huge variability in this regression, and depending on the year that you compute the regression on, you may get plus 30% or minus 30%. But overall, you don't see a significant change. So of course in 2003 and 2007, we had, I think this one is, yes, this one is 2007, we had the overall minimum. But if you look at the immediate, the immediate past, and then what happened later, you don't see any other occurrence, any other clear evidence of reduced water resources availability. But still, if you speak with practitioners, people managing the irrigation consortium, they keep saying that there is a very dramatic decrease. The reason why they say that, basically, is that the river level, this is really decreased, and the river level decreased because of soil subsidence, but not only that, it decreased because they, with the dragging activities, they are taking sand from the river bed, and this caused a dramatic decrease of the river level, about 1 meter in the past 50 years. So if people look at the river level, indeed there has been a big change, but not for climate change, for other reasons. And basically, this brings to me the opportunity to start depicting my take-home message. There is no doubt that we are experiencing changes in water resources availability. And you know, the fact that the river level decreased, it's a big problem because they have the pumps for getting the water that cannot get water anymore. And redesigning the pumping stations, sometimes it's not possible because we don't have money today to do that. So this is indeed a big problem. And also water resources availability is reduced because of increased exploitation, increased usage, and increased pollution. So there is no doubt that we are experiencing dramatic changes. There is no doubt that the future will be a challenge for water resources usage. I think that we will find a solution. I am optimistic because there is enough fresh water for everybody over the world. Not to speak of the seawater, which could be desalinated. So the solution will be found. But indeed, we need a forward-looking vision. And to develop a forward-looking vision, to develop smart strategies, we need to identify priorities. We need to identify the causes for the change, the causes for the fact that water resources availability is decreasing, and these causes should be prioritized. So climate change is indeed something that we have to be concerned of. But what about river dredging? What about pollution? What about increased water demands? What about increased urbanization, which means decreased recharge of the aquifers? So these are all things that matter a lot, and we need to prioritize them. Currently, 95% of the priority is given to climate change, and then it's extremely important for an engineer to understand what is really important. It's important pollution, it's important to increase the water demands or climate change, because the solutions are different. If the problem is climate change, we need to reduce CO2 emissions if we accept that climate change is human-induced. If the problem is pollution, we have to spend the money in other things, in water sanitation plants. If the problem is increased water demands and increased population, we have to spend the money to save water. It's a different approach. The solutions are different. And therefore, it is extremely important to find the priorities. Okay. Now, let me conclude with just one thing. I want to show you a presentation, a talk that I gave just a few slides. Last year, or 2 years ago. This is available on my website. 2 years ago, and I gave this talk in UK. These are some pictures from the Sardinia flood, and I just want to show you. Okay, this was in the Sardinia flood occurred 2 years ago, or 2 years ago, and 17 people were killed. And this picture shows a problem that they experienced. That people were not able to distinguish the roads from the rivers. So some people died because they drove the car into the river because the road was flooded, and therefore they couldn't see really where to go. And so this is considered to be, if you look at the website, the reports at that time, climate change, avian rainfall is deemed to be one of the triggers here. And basically they use the term, they are using in Italy now the term water bombs, which in English has a clear usage. Water bombs in English are what in Italy we call gavettoni. It means that you take a plastic bag, and you fill the plastic bag with the water and you throw it against your friends. And but in Italy we call them water bombs, bombe d'acqua, to mean that we are experiencing now very unprecedented showers, very heavy showers which are unprecedented. Okay, now let's, and also if you look at these graphs, global damages due to floods, you see an increase in frequency of floods and also in the damages. And of course, and this provides support to the hypothesis that climate is changing and therefore causing this increase. And what we did basically, I'm skipping all these reports of recent floods that people tend to attribute to climate change, and I'm skipping this. And you see for different countries, we also did an analysis of the economic losses, but I'm skipping this. And basically, I want to show you, these are the research questions. What are the major causes of the increased flood risk? This is the message that I wanted to give you before. Priorities. And is human impact influencing? This is another question that we try to address. And what monitoring activities can be activated to mitigate the flood risk? And how to mitigate the flood risk? These are the questions that we wanted to address, and of course, identifying the causes is necessary in order to reply to these questions. Sorry, I'm skipping. So the idea was to see if increasing population could be a reason for the increased floods. And in order to do that, we thought to use nighttime lights. And basically, we have NASA and NASA makes available night light intensity data at the resolution of 1 square kilometer for almost all over the world, starting from 92 up to today. And they give an annual value, which means that for each pixel of the world, again, it's very fine resolution, 1 square kilometers for each pixel, they give per each year the average night light intensity. And night lights, they have been proved to be a very reliable indicator of human density. Of course, because humans, when they colonize the land, then they bring night lights. And they have been proved, I state again, very reliable indicators of human density. And the nice thing is that we have time series, we have an annual value for more than 20 years already. And then we crossed the nightline lights with the river network. So basically we have also a map which is extended all over the world where rivers are at fine resolution. This is very simple to do. This is not scientific analysis. It's just putting two layers of information, one over the other. And then we wanted to see what happened in the past 20 years. The idea was to check if the human density close to the rivers has increased. Because we know that in Italy this is one of the main problems. People got too close to the rivers. And then we wanted to prove if this is a worldwide problem or not. And I'm just skipping, this is a picture of Europe, and there must be a detail, no. And we did the analysis at the global scale, the scale of the continents, and at the country scale, to see what happens. And I'm skipping part of the results because they are very technical. Let me see. Okay, this is a picture of the world, of the countries, where we did our analysis. And basically, when you see the red, it means that the human population increased with the intensity that you can see there. And basically, 0 is around the light green and blue. And there is one thing to say, which is the fact that one should know that in some countries they have a lot of space, like the United States and Russia, and the country is not very steep. So basically they have less need to get close to rivers with respect to Europe, for instance. And another thing to say is that some countries started in the recent past a campaign against nightlight pollution. So basically what you see here is that in developing countries and in Europe you see that the density, the human density close to the rivers has increased a lot. In other countries like United States and Russia and even in Central Africa, it didn't increase a lot. So our explanation for United States is nightlight campaign against nightlight pollution. For Russia is the fact that indeed the population in Russia didn't increase so significantly in the past 20 years, and also they don't have this strict need of getting close to rivers. But for the developing countries, And Europe, you see clearly an increase of human density close to rivers. And we looked at the hotspots, like Sardinia, like places in Africa where it's known that the frequency of floods has increased recently. And indeed, in all these hotspots, the color is red, which means that, you know, it's not only climate change that it's important also the human pressure over the rivers, because people get more exposed if they get closer to the river, and then the flood is reported, because if the flood is not significant, it's not reported. And then there is also the problem that if you reduce the room that is available for the river, then of course the river flow increases and you may have a flood where it wouldn't occur if there was no urbanization. And this is a striking evidence that, you know, it's urbanization and river training and increased exposure of people to floods is one of the reasons why the frequency of flood increases. And I think that's it. And also here, it's an interesting thing to see here. It's these are worldwide with different colors for different continents. You can see the economic losses due to floods against nightlight intensity. And you see that there is scatter, but you see that nightlight intensity over the river network, that there is a clear tendency, which is given by the suppression line. There is still a scatter, but indeed you see that the economical damage increases where nightlights are closer to the river. Okay, let me say that I would like to conclude here, to close here, and let me say as a conclusion, and then I will remain available if you have questions today, and if you have questions now. And I also can imagine that you may have questions next week when you start studying and before the exam. So keep in mind my availability. First of all, next week, next Friday is an holiday in Italy. And I'm not sure to be here on Thursday, but I am available Monday, Tuesday, Wednesday. Okay, so if you need any meeting with me, I think the best time Wednesday morning. I am busy, but still Wednesday, not late in the afternoon. Wednesday I would prefer around noon, 1 p.m. And you should send an email to me. But it would be definitely better if you could make an effort, if you need to consult with me, to meet on Monday and Tuesday. Okay, definitely better, because on Wednesday, if there are a lot of students, I may have some problems. And also, of course, I am available later. For those of you who are planning to take the exam in June or later in May, of course, I am available. I just want to make sure we fix also the second date in May. It was 25. Yeah, we fixed it. Okay, perfect. Okay, and before I give the word to you for questions, let me just say a few words. First, when we close, I will be pleased to bring you to the bar and to offer you a coffee first. And second, I just wanted to thank you because this was the first year for this subject in which I could see so many students attending the lectures. So I want to thank you for attending, and the number of students has been quite steady, and this means that you made an effort to attend the whole duration of the course, and I really appreciate that. And also I'm pleased to say that I found a reaction by you that was really stimulating. Good questions, attention, So I'm just pleased to say that I really appreciate your attendance and your participation in these lectures. I'm really glad. So now, let's, if you have questions, I propose that we can stay here whenever, how long you prefer, and then let's go to the bar. Questions? Yeah. Okay, a couple of questions. First.
I would have a question on I model.
Yes.
I didn't understand the graph relating C and FC. The first graph, in particular, when beta tends to 0 and when beta tends to infinite.
Okay, so basically FC is equal to 1 minus C divided C max to the power of beta. Could you check please? Is this one is correct? Okay, perfect. So basically it means that FC varies from 0 to 1 because if okay, C is 0 is 1 minus 1 is 0, and if C is equal to C max, it's 1 minus 0, which is 1. So FC varies from 0 to 1. Perfect. And it takes value 0 when C is 0. It takes value 1 when C is equal to C max. Is this correct? Do you agree with this? Okay. So the only question is, what is the shape of the curve between these two extremes? And the first question is when it is linear. It is linear when beta is equal to 1. Do we agree on this? Okay, because if beta is equal to 1, this graph becomes 1 minus 1, 0, plus C divided C max. So it's linear, because it would be FC is equal to C divided C max. So it's linear. And this is this straight line, beta equal to 1. Okay, perfect. Now let's see what happens if beta is tends to 0. So if beta tends to 0, basically it could be also 0, because it is 0, this becomes FC equal to 0 for any value of C. So basically, what does it mean? It means that if beta is equal to 0, this is the curve. But then here we have a sudden jump, because for C equal to C max, by definition, it has to get here. But this is, you know, if beta equal to 0 is a singularity. Let's say that if beta is very close to 0, what we get is something like that. So this is beta less than 1. Don't we agree? Basically, I want to be clear on what I said for beta equal to 0. Beta equal to 0, this relationship says that FC is equally 0. But, you know, by definition, we define that when C is equal to C max, FC is equal to 1. So this relationship works in the whole range, but not here when, in this particular case, it has a singularity. It doesn't work for C equal to C max. Because by definition, we have defined that C equal to C max gives FC equal to 1, by definition. And therefore, you know, this relationship for the case beta equal to 0 has a singularity in C equal to C max. It doesn't work there. We have to get our definition. But really what I said when I treated the subject was that I never considered the case beta equal to 0. I considered the case beta close to 0, and in this case it works. And you get a shape like this. But in any case, any shape that is below its beta less than 1. And then what happens for beta tending to infinity? Basically, if beta tends to infinity, and given that C, let's suppose C is less than C max, this is a number, the result inside the parenthesis, that is lower than 1, elevated to infinity tends to 0. And therefore, Fc is very close to 1, and then goes rapidly to 1 for C equal to C max. This is what I said. And my suggestion for you, when you have doubts in this kind of doubts on the shape of a function, I think you have two possible ways to clarify the doubts. One is, if you are very good in mathematics, you study the behavior of the function, as I basically did, but my analysis is not really rigorous. You should compute the limits of the relationship, and if you are good in mathematics, this is one way forward. And otherwise, take an Excel file and then just create a sequence of numbers generated through this relationship for varying beta, and you see what is the shape. If you want, I can do that right now and show it to you. The question is
if there is some physical meanings in the difference between beta
yes.
equal 1.
Yes. Of course. The physical meaning is if you get physical meaning is related to the spatial variability of the water retention capacity over the catchment. So what does it mean if you have beta that is equal to 0? It means basically that the catchment, Fc is the percentage of the catchment that has a water retention capacity lower than the given C. So basically, if beta is equal to 0, this relationship here says that this percentage is always 0, so the percentage of the catchment that has a lower retention capacity of the given C is always 0. Then when you get to C max, suddenly jumps to 1. What does this mean? It means that the catchment has a constant water retention capacity which is equal to C max. Or let me say, because I don't have to make confusion between the two cases, it's lower or than C, just 1 second. Lower than C is 0, which means that it's higher. Yes. This is the case in which you have constant retention capacity, which is equal to C max. Because look, if you consider that C max is 200, and you consider the percentage of the catchment that has a lower infiltration capacity than 100, what is? It's 0, because all the catchment has a retention capacity of 200. So this is the physical mean. On the other hand, if you get that the percentage that has lower infiltration capacity of a given C is always 1, it means that the catchment is impervious. It doesn't get any water. And this means that C max would be very small, probably. But it could also be not really small, because you may have the catchment that is 90% impervious, which means that it doesn't take any water, and in the remaining 10% it gets a lot of water. And this means that this curve is very close to the ordinate and then goes rapidly to the value of 1. There was another question there.
Can you explain the denominator of a Nash cycle?
Yeah. Okay. So basically, E is equal to 1 minus, and here you have the summation from I equal 1 to n of x hat I minus xi, and at the denominator I have summation from I equal 1 to n of xi minus the average of x both square. First of all, I'm not sure I used these symbols, maybe I used Q, but anyway, the Nash efficiency, to clarify the context, allows you to estimate how much a simulation is close to the observations. So let me call the simulation x at I, and the corresponding observation is xi. And basically this difference at the numerator is the sum of squares. I take the difference between each observation and the corresponding simulation, I square it, and I sum over the overall n observations. Okay, this is the sum of squares. At the denominator, I have something that doesn't depend on the simulation. It only depends on observations and average, their average. So this doesn't depend on the model and on the simulation. What is this? It's an estimate of the variability of the observations, because when you take the difference between each observation and the average and you square it, this is very similar to the standard deviation. So basically it's something that quantifies the variability of the observations. Now, this variability should be decreased by using a model, because the model makes a prediction. And therefore, the difference between the prediction and the observation still has a variability, but this variability should be reduced with respect to the variability of the observation, because what is the purpose